Okay, good morning again, everybody. Today we're continuing our discussion of definite integrals, and I started by writing on the board kind of like a summary of what we had last time. Let's go over it to refresh your memories. So the question we're trying to answer here is how to calculate the area under the graph of a function. And the method we came up with, well, it's not us, it's more Riemann, is the following. We take the area under the graph of a function. It has to be a bounded function. We're going to include that in the definition, requiring that the function is bounded. If you don't require it, you can actually prove that it follows from the definition, but we're just going to assume it. We're taking the interval, and we're breaking the interval into little subintervals, and this process is called a partition. So a partition is choosing points, x1, x2, x3, x4, etc., and breaking the interval into subintervals. A is going to be called x0, and B is going to be called xn, the last point in the partition. In each of these subintervals, we choose a point. We call them ci's. So c1 is in the first interval, c2 in the second interval. We calculate the value of the function at that point ci, and set that to be the height of the rectangle on the ith subinterval. In this way, we obtain a bunch of rectangles, and we know how to calculate areas of rectangles. It's their width times their height. The width of every rectangle we denoted by delta xi. So the third rectangle, this one, its width is x3 minus x2. That's delta x3. And its height is the value of f at c3. Okay? And then we add up all these areas. We don't get the actual area under the graph because there are errors. So for example, this area here, which I'm now shading in blue, is actually an area under the graph, but we're not calculating it because it's not inside the rectangle. And on the other hand, this area up here is included in our calculation because it is inside the rectangle, but it's not under the graph. So there are errors. This is only an approximation. And this approximation, which we get by summing the areas of the rectangles, is called the Riemann Sum. That's what's written here. Is this so far so good? Everybody? Wonderful. Okay. And then we said, okay, this is an approximation, but we can do better. How can we do better? Make the subintervals smaller. Make a more delicate partition. Refine the partition. That's a term also used, refinement. Okay? So we can introduce another x, and then another c, and then break the rectangle into two rectangles, and that will make the errors smaller. We exhibited that last time. And informally, I'm going to add these quote marks here, informally, the phenomenon that we're trying to capture here is the following. When we make the partition more and more refined, which can be in some sense encoded in letting n go to infinity, making more and more subintervals, then these Riemann sums, the approximations, get closer and closer and closer to the actual value we're trying to calculate, the area under the graph, and we called that I for integral. Okay, everybody? Questions? Okay. And then we defined all these precisely, and then eventually we had this definition of the Riemann integrable, and it says the following. Suppose we have a bounded function on a finite interval. We say that it's Riemann integrable if, and allow me to highlight some things here. For every epsilon, there exists a delta such that if the norm of the partition, this lambda is sometimes called the norm of the partition or the mesh of the partition. If lambda, this is the width of the widest rectangle. Okay? So if we're controlling this width, if the width of the widest rectangle in the partition is less than delta, then the distance between the Riemann sums and the integral is less than epsilon. So if you were to just look at what's written here in these blue boxes, it would really look like the definition of a limit. It would really seem to encode the statement that these tend to I, that the limit of these is I. For every epsilon, there exists a delta, such that if something is less than delta, then the sequence we're looking at minus the limit is less than epsilon. Can you see that? That this is precisely the definition of the limit? Well, not precisely, because there are more quantifiers here. There's this exists I, and for every p, and for every ci. Okay, so that's, we discussed that a bit last time. It's not just letting n go to infinity. Otherwise, we would just have here, there exists an n, such that when n is greater than n, this thing holds and we'd be done. Okay? So let's read it again now and see what the statement is. It's Riemann integrable if there exists an I, that's the integral, that's the area under the graph, such that for every epsilon, we want to guarantee this. For every epsilon, there exists a delta, such that take any partition you want, as long as it's fine enough, as long as it's delicate enough, and that is somehow controlled by saying that the widest rectangle in the partition is less than delta, then no matter what the partition is for every p, no matter what orange points you choose for every ci, look here, these are the orange points. Choose whatever orange points you want. Choose whatever partition you want, whatever xi's you want. As long as the widest rectangle is less than delta, the Riemann sum corresponding to that partition into those ci's, its distance from the actual area is less than epsilon. Okay? That's the definition of the integral. It is a mouthful. You have to think about it and see how to absorb everything. But I think if you can just kind of match the idea with the intuitive drawing we had over there, that's sufficient for us. We're not going to actually prove things with this formal definition. Okay? Now, I want to make several remarks. So let's write remarks. Remarks. One, if I exists, and we're going to see that it doesn't always. We're going to see examples in a minute. If I exists, then it is unique. So that's our first remark. It's kind of the uniqueness of the limit statement. Okay, we're not going to prove this. That's why I'm just calling it a remark. Remark number two. If f is integrable, is Riemann integrable, saying if I exists, if this is the case, then we denote the integral, and say goodbye to I, because now we're going to have a new notation. It's going to be a snake. There are going to be a and b, a down here and b up here, and then there's going to be f of x dx. This is the notation we're going to use. Okay? This s, we're going to discuss it a bit later in a bit more detail, but this s actually comes from sums, from the letter s, from an ancient form of the letter s in Latin or German, and it comes from the word summa, sum. Okay? And we'll discuss it a bit later. Okay, so it's a limit of sums. We think of it as continuous sums. Okay, and we'll see why this is the correct way of thinking about it. So this is the notation. And remark number three, So we met the snake before, right? This was related to antiderivatives, something which is really should belong to the previous part of the course, to differential calculus, right? So that's where the snake showed up, and the connection to these antiderivatives, to these so-called indefinite integrals, which didn't have the a and the b. So this connection is deep. Deep in the sense that it's not trivial. Okay? It's surprising. It's not something you think of right away. Surprising.
The connection with the A and the B and without?
Yeah, the connection of this notion, which in your mind should say area under graph, and this notion, which is antiderivative, how are they related? These really should have been denoted by completely different notations. Okay? But they're denoted very similarly. Okay? And the reason is that they are connected. They are very relevant to each other, but this connection is not something trivial. I can't state it now. I'm going to state it, but it's going to be later today, after 15 more theorems. Okay? So it's deep, surprising. Give me more superlatives. Nah, that's cheating. Other superlatives.
Shocking.
Shocking. Good. Well, that's kind of surprising. Okay? Okay. Deep, surprising, whatever superlative you had, and to the extent that it's called breathtaking. Wonderful, wonderful. And it is called the fundamental theorem of calculus. And we will discuss it. We will discuss it in about 2 hours. Okay. Okay. So for now, we're still in our amnesia part. We're not discussing these, and we don't remember what they are. Okay. But we are going to use this notation from now. Okay. And remark number 4 is it's actually a definition. So we define the integral from a to a of f. This you can think of intuitively as the area under a point. Okay? But remember, the whole area business is just motivation. The formalism is the formal definition. So we define this to be 0. Okay? And another thing we define is, in the definition, we wrote, or not the definition, when we wrote I equals the integral here, we said we're going from A to B. So somehow implicitly A is the left end of the interval and B is the right end. If you want to go from B to A, if you want to write this, so this is defined. By definition, it's defined to be minus the integral from A to B of f. Okay? And we'll see that this fits in perfectly and works perfectly with things that we'll do later. So this is a definition. Both of these are just definitions. Okay. So what I want to do now is actually calculate, using Riemann sums, some areas under graphs. Okay? So examples. So example 1 is going to be f of x is going to be a constant function. So here's A, here's B, and we're looking at the function, at the very boring function, which is just constant c on the entire interval. Okay? Now, the area under the graph of this function between A and B is in fact a rectangle. We know what the answer should be. What should the answer be? Right, b minus a times c. Does everybody agree? So we know what we're expecting here. Let's see that we actually get it using the definition. Okay? So for any partition you do of the interval here, any choice of xi's, and for any choice of ci's, no matter which orange points you choose to evaluate the function at, you're going to get precisely the same Riemann sums. You're going to get, we get a Riemann sum of the form sigma I equals 1 to n depends on the number of points you chose to divide by. And then we get, look at the Riemann sums. Where are the definition of the Riemann sums? These things, right? These are the Riemann sums. We have to calculate the value of the function at whatever the orange points were and multiply it by the width, delta xi times f of ci. What is f of ci? Whatever the orange point is, what's the value of the function at the ci's? It's always c, because the function is always c for any value. So we get c, this is f of ci, no matter what ci is. Do you agree? Times delta xi. These are the Riemann sums. Do you agree? Since c does not depend on I, we can pull it out of the sigma. Okay, so this equals c times sigma of delta xi. And what is the sum of the lengths of the subintervals? It's the length of the entire interval. Do you agree? So we get c times b minus a. Does everybody agree? So it doesn't matter what partition you took and what ci's you took, the Riemann sum always takes the same exact value. And of course you can see it intuitively. Take a partition. What's going to be the sum of the areas of the rectangles that you get? It's going to be this. There's no error. Do you see that? Okay? And of course in the limit, if you're looking at the same value every time, take the limit, it's still going to be this value. Okay? So the conclusion is the integral from a to b of a constant dx equals the constant times b minus a, which is what we expected intuitively. Clear? Questions on this? Let's do another example, slightly more intriguing. Let's erase these remarks for now. This was our first example. Give me a chance. Example 2. Our all-time favorite function, the Dirichlet function. 1 when x is rational, 0 when x is irrational. Do you all remember the picture? Well, the so-called picture of this Dirichlet function. It's just like a bunch of dots on 1 and a bunch of dots on 0, and we said that that is not an accurate picture in any sense, right? Okay. What's the area under the graph, intuitively? Okay? It's not clear, right? Is the area 0? It's just a bunch of dots, but there are many, many of them.
It's not Riemann integrable.
Right. That's what's going to turn out. We'll see it in a minute. This function is not Riemann integrable. Okay? There's no real meaning in the formal sense we defined to the area under the graph of this function. Remember, this function is Let's look at it on the interval 0, 1. Okay, so here's 1, here's 0, and the function was something, okay, something that I can suggestively draw like this, but it's not even clear what this drawing means. We know what we mean to draw, but this picture is not accurate in any sense. Okay? So I want to show formally that this function is not Riemann integrable. And let's see why that's the case. For any partition you take whatever partition you want. Now you have to choose the orange points, right? That's the next step. You take a partition, then you have to choose the points where you evaluate the value of the function. If we choose CIs which are rational, if we choose all the orange points to be rational, and we can always do that. In any subinterval, no matter how small it is, there is a rational number. Remember? Why is that true? Right, because of the axiom which we call the axiom of completeness. Remember? No matter how close, how small the interval, there's going to be a rational number there. Choose your orange points, the CIs, to be all rational. If we choose CIs in Q, then the Riemann sum we're going to get is going to be what? Sigma. What is f of Ci if Ci is rational? 1. Because the value of f at rational numbers is 1. So we get 1 times delta xi. I equals 1 to n. Which is what? It's 1. The 1 we can just erase or pull out of the sigma if you want. It's, again, the sum of the lengths of the subintervals, which is what? Right, it's b minus a, but we said we're looking at b equals 1 at a equals 0, so it's the length of the interval. It's 1. Do you agree? So if we choose all these orange points to be rational, we get a Riemann sum equal to 1. No matter what partition you choose, no matter which actual orange points you choose, as long as they're rational. For the same partition, if we choose irrational CIs, CIs which are not in Q, we get a Riemann sum, which is sum I equals 1 to n for the same exact partition, just a different choice of orange points. What is the value of f at irrational points? 0. So we get 0 times delta xi. In other words, we get 0. So for any partition you take, any partition, you're going to get 1 or 0 as your Riemann sums, depending on if you choose rational orange points or irrational orange points. And if you choose some of them rational and some irrational, you're going to get numbers in between 1 and 0. Okay? So it's not going to hold that by controlling for the width of the biggest rectangle, that by forcing your partition to be refined enough, that by forcing the partition to be delicate enough, in other words, if you look at the definition, no matter what delta you take, by forcing the norm of the partition to be less than delta, you cannot ever hope to obtain something like this. You're going to have your sum of these be zeros, depending on the CIs, and some of these be ones. They don't, a sequence or a more general thing, but even think of a sequence. If some of its elements are zeros and others are ones, it's not going to converge to anything. Do you agree? So the conclusion is there exists no I that would satisfy this. There is no I, therefore it's not Riemann integrable. So the conclusion, f, the Dirichlet function, is not Riemann integrable. Questions? So the role of this Dirichlet function, it's still continuing to bravely play that role as we proceed, is of kind of showing that things do not necessarily always go the way your intuition is working, because not all the functions are the way your intuition is. Not all the functions are elementary. Not all the functions are nice and smooth. Some functions are Dirichlet and variations. Okay, clear? Let's do another example. So example number 3. So I want to do an example where we have a calculation that's a bit more interesting than just saying the Riemann sums are always the same. So example number 3. Let's take the function f of x equals x on the interval 0, 1. So here's 1, here's 0, here's 1 up here, and the function is just this. So this is f of x equals x. And we want the area under the graph. It's a triangle. We know what we expect, right? We expect 1 times 1, which is 1, times 1/2. So we expect the answer to be 1/2. Do you agree? Okay. So let's see how we do it with Riemann sums. I'm going to cheat a bit, just a bit, in the following sense. I already know that this function is integrable. I'm not going to prove that. Okay? The reason that I know that it's integrable is because of theorems that we're going to write in just a few moments that say, for example, any continuous function is integrable. This one is continuous. Any monotone function is integrable. It's also monotone. Okay? So I know that it's continuous. I'm not going to prove the existence of I, of the integral. I'm just going to calculate it. Okay? So how do I calculate it? So I'm going to write partitions. Okay? What partitions am I going to write? Well, since I know it's integrable, the statement of the definition says take any partition you want for every p. Look on this board. For every p, blah, 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 blah. So I can actually choose my partitions as long as they satisfy that their norm, that the width of the fattest rectangle is less than some delta, then I know that the corresponding Riemann sums are going to get closer and closer to the integral. Okay? So I'm going to choose a sequence of partitions which satisfy this. Namely, I'm going to divide the interval into equal parts. That's the easiest thing to do. How many equal parts? Well, 5. But then I'm going to refine it and say 6. And then I'm going to refine it and say 7. It's not really refining. I'm not dividing rectangles into parts. I'm just taking the entire interval, first dividing it into 5 parts, then 6 parts, then 7 parts, then 8 parts, equal size. Okay, so let's write that. Divide the interval 0, 1 into equal subintervals of width 1 over n. So I'm going to divide it into n subintervals. Here is going to be 1 over n, this is going to be 2 over n, 3 over n, etc. N subintervals. Okay? in each subinterval, so this is the partition I'm taking. And you can see that by making n bigger and bigger, I can make the norm smaller and smaller. The bigger the n, the smaller the norm. Do you see that? Okay. Now I have to prescribe the orange points, right? The points where I evaluate the functions. So in each divide into subintervals of width 1 over n, and each take ci to be I over n. So I over n, C1 is 1 over n. This is the first interval. C1 is 1 over n. So I'm just taking the right endpoints of each subinterval. The right endpoint of each subinterval. And then I'm calculating. So where's my orange? Here it is. So I'm taking this point on this interval, calculating the value of the function. Here, likewise, and so on. So what are the rectangles that I get? The rectangle picture is going to be, in this case, like this. Do you agree? In each subinterval, I took the right endpoint. So the rectangles I get kind of add some extra stuff which lies above the graph. Do you agree? Can you see that? It came out a bit small, but can you still see it? Okay? Okay. So let's write what we get. So we get the Riemann sum, the corresponding Riemann sum is what? So we want sigma f at ci delta xi. That's the Riemann sum. Let's see what we get here. So we have sigma I equals 1 to n. We get n subintervals. What's f at ci? The ci's are I over n. So let me write f at I over n times delta xi. What is delta xi? What is the width? It's 1 over n. All the intervals are of the same width. They're all of width 1 over n. Do you agree? So I'm going to multiply this by 1 over n. And now, sigma I equals 1 to n. What is f at I over n? What was f? F of x is just x, right? So f of I over n is just I over n times 1 over n. Do you agree? So this is, let's simplify it just one more time. The n's do not depend on I. So there's a 1 over n squared that I can actually pull out of this, right? And then I get sigma. Of course I can. But I can pull it out of the sigma. The sigma is a way of writing a sum. A sum, the first term in the sum is going to be 1 over n squared. The second term is 2 over n squared. The third term is 3 over n squared, all the way up to n over n squared. The 1 over n squared I can pull out, and it's just the sum of I. 1 plus 1, 2 plus 3 up to n. Do you agree? Everybody good? So the Riemann sum corresponding to this specific partition with this specific choice of CIs gives me this. Can I simplify this further? What is the sum I goes from 1 to n of I? This is just an arithmetic sequence, right? Well, a finite arithmetic sequence. 1 plus 2 plus 3 all the way up to n. What is its sum? No. No, not a product. Sum.
We have this more serious. It's 1 plus n times 1.
Exactly, right. So there was a formula for the sum of, so it was, in general, it was a1 plus an, the first element, plus the last element, times n over 2. Remember that? So a1 is 1 here, and an is n, so it's n plus 1 times n over 2. But there's the 1 over n squared that I have to carry along. So I get this. Okay, good? And this equals, one of the n's can cancel, so I get what? N squared plus n. So I get n plus 1 over 2n. Do you agree? Yep. So this is the approximation by rectangles that I get if I take partitions in which I always divide into equal subintervals and always choose the right endpoint for each of these subintervals and calculate the sum of the areas of the rectangles. Right? What does the definition tell me? Make the partition more delicate, reduce the norm, you approach the limit, which is the integral. So by making n bigger in this case, I reduce the norm. I make the interval smaller, right? And when n goes to infinity, and in this case, it's the honest limit n goes to infinity, which I know exists because I know the function is integrable. What do I get? What's the limit of this thing? 1/2. Chorus. Good. I like that everybody knows their limits. Good? So this is the I. This is the integral from 0 to 1 of the function x dx. Questions on all of this? The one thing everybody should agree is that we really don't want to do this for functions which are any more complicated than x. This is tedious. Do you agree? This is, well, we said we're always having fun here, but you can see that this is not going to be that much fun if we try to do it for arctan or for I don't know what. Okay, and let alone functions that have complicated formulas. This is a lot of work. Do you agree? So we somehow want a better way of evaluating integrals. Right? So what we're going to do now is write 15 theorems, approximately, that are not going to help us. That are going to summarize properties of integrals, which are very useful and we're going to use a lot, but they're still not going to give us the answer to how to do this more efficiently. How can we avoid altogether taking Riemann sums and finding their limits? Okay? And the answer to that is going to be that all mysterious, exciting fundamental theorem of calculus, which is going to appear only after we set the ground for it, which is the theorems that we're going to discuss now. Okay? So we did a few examples. We know that sometimes the integral exists, sometimes it doesn't. I want to make two more remarks before we start writing theorems. Remember here when we discussed the intuitive question that we're trying to answer, we said the fact that the function is bounded and that the interval is finite, those are essential. The fact that we're drawing it positive and continuous, that's not essential. Okay? I want to show you what happens, for example, if you take a function that's not positive. Okay? So suppose we take a function that's not positive. Here's A, here's B, and suppose our function, I'm still going to draw it continuous to make it easy to look at. Suppose the function looks maybe like this. Here's f. And I'm not going to draw all the little details like here, because I just want you to get the idea. How do I calculate an integral? Using the definition. Okay, I'm taking a step beyond the intuition and saying, okay, what's happening by definition? I'm going to break this into subintervals, take a partition, and then in each subinterval there's going to be an orange point at which I'm going to calculate the value, and that's going to give me the rectangle. Do you agree? Whenever there's a subinterval, here's a little subinterval here, where the function is negative. So the point I'm going to have, the orange point, the value at that orange point is going to be this. So what I'm going to get is the width of the subinterval. That's still going to be delta xi, whatever those i's were. But the value of the function is going to be negative. So the contribution of this rectangle to this sum is going to be the value at that ci, which is a negative number, times the width of the rectangle. The contribution at a point where the function is negative is going to be an area in minus. Do you see that? Do you agree? So what's going to happen is, when I calculate the integral, and when I refine the partitions, and when I go to the limit, what I'm going to get eventually, let's draw this one more time, what I'm going to get is that for areas where the function is positive, here's our function. Here's our function. For areas where the function is positive, I'm going to get the area under the graph. So for this subinterval, I'm going to get the area under the graph with a plus sign, just like in this case. But here, I'm going to get the area not under the graph, but I'm going to get minus the area above the graph, but below the x-axis. That's what I'm going to get. And here I'm going to again get the area with plus. That's what this notion is going to give me. It's not going to give me the sum of the areas under the graph, because under this graph, the area is what? Infinite. The whole graph is under the x-axis, right? I'm going to get this area in plus, minus this area, plus this area. Do you see why that follows from the Riemann sums? Why areas where the graph goes under the axis contribute negative contributions to the Riemann sum? Do you see that? Okay, so that's what I'm going to get. Everything is going to be the same in the definition. Everything is going to be fine. But I'm not going to get the area under the graph, because it doesn't make sense to talk about the area under the graph. This is what I'm going to get. Clear? Okay. When the function is not continuous, everything is still going to work just the same. So if the function is not continuous, maybe it's 1 here and 2 here, you're going to get the sum of the areas in this extended sense. Okay, so everything is going to work. There's no requirement for the function to actually be continuous. Okay? You know we can calculate sums of areas. Suppose the function is 1 here and 2 here. It makes sense to talk about the area under the graph, right? So all these facts follow from the definition. I'm not proving these things. I'm just giving you the intuition. Okay? So the first statement, so I'm going to write a couple of theorems, then we'll have a break, and then we'll write some more. So let's write the first theorems. So the first statements are the ones that I already used, namely the following. So theorem: if f is, this is an if statement, doesn't necessarily happen, but if f is piecewise continuous, or piecewise monotone, then, did I get the I and the E in the correct order?
No one ever knows.
No one ever knows, that's true. But does somebody know? It's correct? Good. So, if f is piecewise continuous or piecewise monotone, then f is integrable. Piecewise means that you can divide the interval into subintervals, finitely many subintervals, and on each of these subintervals, f is continuous. So it means that it can have a finite number of discontinuities. These discontinuities can either be of type jump or removable, or essential of the oscillating type. They can't be infinite discontinuities because we said the function is bounded. All our discussion is for bounded functions. Okay? So if f is of course bounded, because that's our discussion, that's the realm of this entire definition, bounded functions. If it's piecewise continuous, finitely many glued subintervals on each of which it is continuous, or piecewise monotone, like sine of x. Sine of x is piecewise monotone. On any finite interval, it goes up, then it goes down, then it goes up, then it goes down. That's piecewise monotone. It's not monotone, right? But it's piecewise monotone. Then it is integrable. Question?
Yeah. What is about the Dirichlet function with x and minus x?
The Dirichlet function, no matter which interval you take, and no matter which variation you take, x and minus x, x squared and minus x squared, it's not going to be monotone. You cannot, or continuous. You cannot divide the interval into finitely many subintervals on each of which the function is monotone. No matter how small an interval you take, it's going to look. Do you agree? So it doesn't satisfy this, and there's nothing you can do to save it. Okay? This seemingly what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 words hide 2 hours at least of lecture in order to prove them. At least. This is not a trivial statement at all. Proving, even if we make it easier, even if we just to prove that a continuous function is integrable, takes a detour, requires a detour through a term that we didn't even mention here, okay? And we're not doing it. So just keep in mind that if you ever need to somehow go deeper into these notions, that we're really saying it, believing it, and not doing the actual work that's required here. Okay? So these are non-trivial statements, but we're going to use them. So once you know that a function is integrable, you can do these tricks that we did in the last example. You can choose whatever partitions you want. For example, divide it into equal segments, which is the easiest thing to do. You can choose whatever points you want. The orange points. You can take always the right ends, or always the left ends, or always the midpoints, or always the points where the function gets a maximum, or always the points where the function gets a minimum, whatever way you want. As long as you make the interval smaller, you're good to go. You know that the limit, as n goes to infinity, is going to be the integral. That's the statement that it's integrable. If you don't know that a function is integrable, you first have to prove it, and that's hard. Okay? So this gives us for free the fact, well, not for free, somebody has to do the work, but this gives us for free the fact that for continuous or piecewise continuous, monotone or piecewise monotone functions, the integral exists. And you can do all these tricks. Okay. By the way, one more little statement and then we'll have our break. By the way, one can actually characterize integrability in terms of continuity. Okay, it's a more sophisticated statement that tells you exactly when a function is integrable in terms of how many points of discontinuity it has. Okay, and how many is kind of vague, because if this tells you that if it has finitely many points of discontinuity, it is integrable. That's hidden in this statement, right? But it's not an if and only if statement. It could have infinitely many points of discontinuity and still be integrable, but that infinitely many points of discontinuity can only be big to a certain extent. And that goes into notions coming from measure theory. Okay, so it can only have what's called Lebesgue measure 0 points of discontinuity. The Dirichlet function has also many points of discontinuity, but too many of them. So it's not integrable. Okay, so there exists a characterization of integrability in terms of how big the infinity of discontinuity is. That's beyond the scope of this course. Okay, so let's have a 10-minute break now, and then we'll continue.